After I posted a bunch of pictures on Twitter the other day about some of my homemade PCBs, a bunch of you guys emailed me and asked me if I could make a video on it, and I thought, sure, why not? So first off, the method I'm using is called Photoresist Method. There's a bunch of other methods out there, and let's just go over that real quick. You can, of course, use regular copper-clad boards, and they exist in all sizes and shapes, and just simply draw your traces on there with some sort of permanent marker that protects the copper from etching. That's the simplest method, and it is efficient if you have a good hand and can draw moderately straight lines on there. So if you've seen some of my drawings, you know that's definitely not a method that works for me. Then there's what's called the toner transfer method. That's really popular right now, and it's basically you take a laser printer, print your circuit design on a piece of paper, like so, but this is not the right paper. You can't, well, I guess you can, but you shouldn't use regular paper for that. There's special paper that you would want to use that's glossy and very thin. But anyway, you would put your printed circuit board, just a bare copper clad like this, on this side where the toner is located, and run this thing either through a laminator or some sort of iron or whatever you want, any heat source pretty much. And what happens is that the toner melts again and sticks on the copper, and you can just then stick it into your etching solution, and basically wherever the toner is attached to the copper, the etching solution can't get to the copper, so only where you have exposed copper, you will actually remove the copper from the printed circuit board. And that's a really nice method, works very well. I've been using it for a long time, but I like the photoresist. So photoresist uses copper clad boards that are either pre-coated in photoresist paint, or you can buy photoresist paint like this German example right here and spray it on your own printed circuit boards. Now if you're just doing stuff with regular FR4 material, and this is the most commonly used material that you'll find on your regular copper clad, it's no problem to buy them pre-coated with photoresist. That's absolutely no issue at all. They're junk cheap, you can just buy a chunk of them. I tend to buy them in this European size 100 by 160 millimeters. I have tons of them and I go through them like crazy. I have single-sided ones and I have double-sided ones. Looks like they're all double-sided, but I have them both. And anyway, that's no problem if you just work at lower frequencies. If you buy stuff like this, and that's an example of a microwave substrate. This is Rogers 4003C material that works very well into the upper gigahertz range. It has a ceramic substrate right here. You cannot, at least I haven't found a source, you cannot buy these pre-coated with photoresist, and that's pretty annoying. Like I said, the spray is nice, but I have always had difficulties actually getting a very solid and uniform layer of photoresist on there. I don't know if somebody has a secret trick on how to do that, please let me know, but for those substrates I am actually using the toner transfer. Now anyway, what we want to do is we want to get our layout. I simply made out a simple layout like this. This is what we want to use for this experiment. We want to get this on a piece of FR4 material like this. So all we have to do is print our circuit board on some sort of transparency and expose the PCB. We have to remove this layer right here, this bluish protective film, and put a light source above it and make sure that this is laying on there the way we want it to, and expose it. But before we get into that, let's talk safety. Obviously you're gonna be working with chemicals to develop and etch your printed circuit board. And chemicals, every time you play with them, if you don't know what you're doing, be super careful. Sometimes it's really not immediately apparent what might happen. A great example here is that the developer that you can buy, this is from MG Chemicals, just standard stuff that you can buy from Mouser or DigiKey, and this is based on sodium hydroxide. And then we have the etchant, which is based on ammonium persulfate. And this thing is corrosive and oxidizing, and sodium hydroxide is used as pipe cleaner. It hurts if you get it on your skin, but it won't kill you. Be careful to not get it in your eyes. But a great example of unpredicted reactions that might happen. If you mix those two together accidentally, you're going to release ammonium gas, which is really not very nice in your eyes and your nose. So it's a great example of, if you don't know what's happening, be very careful. And there are some examples. For instance, some people like to etch with hydrochloric acid instead of ammonium persulfate, and they add sodium hydroxide to just enhance the etching process. And then they use acetone, like in nail polish remover, to actually remove this film, either in the toner transfer, the actual toner, or the film. After you're done etching, you need to remove it before you solder, of course. So they use acetone for that. And if you mix hydrochloric acid, hydrogen peroxide, and acetone, you're actually creating, by accident, something that is capable of exploding quite well. Now anyway, here's the safety warning. Use glasses, and I didn't find my transparent glasses, so I'm using the yellow ones, the laser ones for illustration. A pair of gloves at a minimum. And be careful what type of clothing you're using. And I have this shirt here that I was wearing the last time I was doing some of the etching. And as you can tell, this formerly very nice blue shirt is now at best something for the garage for doing an oil change or something like that. So be careful. This is one of those typical don't try this at home disclaimers. Okay, let's get started. The first thing we have to do, of course, is to expose the PCB. But right after we do that, we need to develop it. Obviously, we don't want it to lay around and catch more light, and therefore we want to be able to toss it directly into the developer. So let's start with that. I have about 200 milliliters of water right here, and this is supposed to be our development solution after it's done. And we simply follow the instructions on the developer itself, and it says we need to add 1 part of this to 10 parts of water. Okay, so I have 200 milliliters of water there, so I need to add 20 milliliters. I'll measure this out in this little beaker here. 20 milliliters. There we go. And when you dilute acids or bases, please always pour the acid or base into the water and not the other way around. And please also put your gloves on first, and don't just do it barehanded like I just did. The reason is, if you pour the water into the acid or base, you're going to have a lot of heat development. Sometimes the heat development is strong enough to get the acid or base that you're diluting to actually boil and splatter all kinds of stuff into your eyes or in your face in general, and that's really not a nice feeling. So all we're going to do now is pour the solution in there. And that's going to be our development solution. And I got this nice little container here for developing. Just going to pour this in there. And again, imagine me wearing gloves, since I gave you a big lecture on this. That's that. That's our developer that we're going to be using. So let's move over to my exposure setup and see how we expose the PCB, and let's develop it right afterwards. So what I'm using here is a really cheap exposure setup. I bought it from, I think, Mouser Electronics, and I don't know who the original manufacturer is, but it's basically a standard 15-watt fluorescent light in here on a couple of spacers, and it works surprisingly well. If you want to do better, there are nice exposure frames that you can buy for relatively little money on eBay or, well, anywhere else. And well, the way you want to do this is you want to remove this blue cover here. Then you want to put your transparency with your artwork directly on there. And to make sure it's actually on there snug and even, I have this transparent piece of plastic, and you just put that on top of there. So that's really all the magic behind it. And then you want to start the exposure. Now, this is not really good advice to switch it on just before, because fluorescent lights gain intensity as they become warm. So what I do when I'm not shooting a video, I'm actually letting this thing run first and just remove it, set up my PCB, and then I move it in, and works very well. The exposure time for this PCB is about 10 minutes. and that's something you need to find out by experimentation or by the documentation given with your PCBs, depending on where you buy them. So let's take off the photoresist cover here, the protective film, and let's get it in place. So we don't have to work extremely fast, but we have to be time conscious. So the only reason I'm leaving the exposure light on is because the intensity of the film lights I'm using is much higher anyway, so if it screws up, it'll screw up regardless. So exposed, that's where we want it to be. Looks about right. I'll put on my plastic cover here. Move that back over there. And start the timer. Now let's wait 10 minutes. Okay, 10 minutes are up. So let's remove all of this and move our exposed PCB over into the developer solution that we have made beforehand. Let's zoom in so that you can see a little bit of the reaction. And the time really depends on how strong the developer is and a bunch of other parameters, but you'll clearly see it developing. And on a side note, you don't really need to buy this pre-made MG Chemicals developer. It's simply sodium hydroxide, so you can buy sodium hydroxide for fairly cheap, and I think the ratio is 1 gram per 100 milliliters. And I got my gloves on now. Please don't do it the way I'm doing, but I think plastic tweezers would be a whole lot better. Just agitate it a little bit and you will start seeing the traces coming out there momentarily. Time's usually somewhere around a minute, minute and a half. Like I said, depends on how hard you exposed and how strong your developer is and a bunch of other parameters, but you will clearly see it developing. So basically, and you can help it a little bit and go over there. There are apparently some brushes that you can buy that are specifically made for making the photoresist disappear where it's supposed to disappear. Okay, now you can clearly see something happening, and I try to help it a little bit and go over there with my gloves. Like I said, there's an extra sponge to do that. It's like brush type with a sponge at the end. And alright, that looks very nice. I think we're done here with the developing. Let's see. Yep, that looks all very sharp. Drop it in some water. Obviously you don't want to continue developing it after it's done, else you may overdevelop, and you don't really want that. Okay, very good. Alright, now this is what it looks like. You can clearly tell that we have a super sharp image on there, and basically what happened and what's going on now is that we have this paint, this photoresist paint over the areas that we do not want to be etched, and the paint, the photoresist paint, got removed where we want the copper to be etched away. So all we really have to do now is find etching solution and etch this printed circuit board. This is really all the magic behind it. No secret tricks. That's it. It's really as simple as that. So let's rearrange the workbench and let's get the etching process going. Okay, for the etching process, I like to use ammonium persulfate, and it's probably less popular in the hobbyist community. In the hobbyist community, what's often used is ferric chloride. The only problem I have with it is that it stains so bad. If you get it on anything, clothing or your workbench or again anything, it really stains very, very bad, and I don't like that very much. I already get in trouble enough for getting all my shirts ruined and messed up, so I don't want to add on to this. So what I'm using is ammonium persulfate, and I'm actually using this little etching apparatus here. And basically, it's something you could build at home from transparent plastic, no problem. It has a normal aquarium air pump, a hose to the bottom, and this diffuser pipe here on the bottom. It's just making sure that you get movement into this water. than a standard aquarium heater that brings the temperature of the bath up to about 40 degrees Celsius. And you get this neat little holder here, and I added 2 stripes of tape on there to make sure my PCB stays where I want it to be, kind of centered, and a rubber band on the bottom to make sure there's some tension on there. That's especially useful if I have more than one printed circuit board at the same time. So now let's put it in here and see what happens. Alright, something went wrong with my demonstration PCB. I have 2 guesses. Number 1 is that I used old PCB material. I think the PCB material that I used is over 2 years old, and it appears that there were some issues with that. Issue number 2 is I probably scrubbed a little bit hard on the photoresist with my gloves on, but that's no problem. The great thing about being a content producer is that you can always move on to something different and just continue. So trust me, everything I said does work. You just have to not scrub so hard on it, and using fresh materials is a really important thing. This is true for all your chemicals too. You really just want to mix your developer and your etching solution together when you actually need it, not have that stuff standing around for weeks or even months. You want to use fresh printed circuit board material. So when you buy, make sure you only buy as much as you will reasonably use in a certain amount of time so that it doesn't really go bad. But no problem, with the exact same method I did make this printed circuit board and this one up here also, but this is the one we're going to have a look at. So after your etching is complete, this is what you're going to end up with. And obviously there's still photoresist all over this. This was used to protect your copper layer from being etched away, and now you want to remove it to expose the copper. And I always wait very close to the time when I actually solder the PCB, just to make sure that the copper is protected and doesn't oxidize. So the way of removing this is using acetone and just rubbing it off. And acetone, I always steal my wife's nail polish remover here, and if you've watched my videos long enough, you know that I frequently steal things out of her arsenal of things, and so that's very useful. The worst thing is getting caught, but anyway, so you just apply a little bit of acetone to anything. In this case, I'm just using a towel that I have been using for that. Now let's just take about half of it off, and you can see photoresist is still on over here and it's off over here, and the copper is exposed. And it's gone, and we got a beautiful printed circuit board. Like I said, I used the exact same methods and everything that I have shown you in this video. The printed circuit board that we made together probably messed up for a bunch of different factors, so don't really worry about that. Don't be discouraged. And this is also a great thing to show that there are things that you can mess up in a video. But anyway, so that immediately shows you a couple of things that you need to carefully watch when you do these things. And one is freshness of your material, and the other thing is that you watch your timings and your concentrations of the substances, that you make sure you use the proper amount that you're supposed to use, and that you read the manual for the PCBs and make sure that you're using correct exposure time, and that you're using the correct amount of etching time and all that sort of stuff. Now, there's a couple of things I want to mention. Obviously, we just scraped off the protective layer here, and that was previously protecting the copper from oxidizing. Now, let's say you change your mind and you figure out that you're not going to be able to solder this PCB for a couple of weeks or month. So what can you do? Well, there's some spray paint, solderable spray paint. And again, here's a German example of that. You can buy that pretty much anywhere. I know MG Chemicals make some of that also. You just spray it over there. That's a protective coating, and it makes sure that your copper stays neatly protected, but you can solder on it, no problem. And the other option is tin plating. So if you ask, can you tin plate at home? Yes, absolutely, you can do this. And here's one example. This is a liquid that you can buy from MG Chemicals, and there are some powders out there too. It's the same stuff basically in there, but there's two reasons I don't use it. Number one, I don't really need it, and number two is that those chemicals are really not very nice. They are something that you really don't want to be around unless you absolutely have to. So if you can avoid tin plating, do avoid it. And that was it. That was just a quick intro on how to do photoresist. And remember that this is just my way of doing things. And you can really vary many parameters, like the exposure. Some people use a regular light bulb. Some people use sunlight. And there's so many different ways of doing things. There's different developers. There's different etchings. There's different everything. So this is one way of how I do things. And I hope it helped you a little bit. And one thing to mention before we finish up here is drilling. Now, the PCB that I previously made with you guys only had SMD pads on it. But obviously sometimes you need to have some sort of through-hole holes. And well, all you buy yourself is a little drill set like this. And one of those small handheld drills. And you just drill the holes. There's no magic behind it. And this brings me to a design question. Obviously, if you're drilling these tiny holes on your own at home, you want to make sure that the ring around the holes is a little bit bigger than you would normally design it. And this is something to really pay attention to. If you do stuff at home, try to define your design rules so that they are favorable for your do-it-yourself conditions. So big rings around the holes, big pads. Try to avoid tiny traces. Try to avoid just itty-bitty tiny etching things between traces. I mean, here, this is very sharp. This looks very nice. But if you would try to make it too small, you would probably get issues. And in this case, this one are down here and that one here, they are controlled impedance microstrip lines. In this case, the distance between the copper layer is very important. So you may be tempted to just put in whatever values your software gave you to get that certain controlled impedance. But in reality, you really want to make sure that those values are doable with your do-it-at-home, do-it-yourself technique. And obviously, you're going to be doing it somehow different than what I'm doing, and that's perfectly fine. But in that case, make yourself some sort of test PCB and just play around with it. Just try it out. By the way, here's an example of a Wilkinson divider that I did. By the way, this is just single-sided, so this thing isn't worth much. Obviously, you need a copper plane on the back, but there was a test that I did. And it's just an example of so many neat things that you can do at home with PCB material. And the important thing about this is experiment. Like I said, your conditions are going to vary from mine. And like this video has shown today, even doing things under the same conditions every time may change the outcome if just a single variable is different. In this case, it was probably the age of the PCB material. So be aware of that, do testing. And another thing I usually do is always do twice as many PCBs as I need. If I need 2, I'm making 4. If I need 3, I'm making 6, always. Just to make sure that single errors, simple things like overexposure or over etching are not an issue. And if I catch them in time, I will still have the amount of PCBs that I need. And if I have some extra, it's just nice safety that if I don't screw something up in the soldering process that I'll have to go back and set everything up again, then I can just go back to that one PCB that I have spare